Yeah, first speaker this afternoon is Farzin. Please, yes.
All right, thanks very much, and thanks to the organizers and for the opportunity. I'm going to talk about complexity and multipartite entanglement in quantum networks. This is going work with Andreas Windberg, and as you might have noticed, paper appeared on our podcast this morning. We're going to talk about, we want to understand noisy entanglement in a general mixed multipartite mixed state. We have this state here shared between A1 and A1A legal parties, and there's the state of environment, which may or may not be purified state. Now we want to understand entanglement content of this state and how much classical or otherwise quantum correlation exists in this state. In single shot case, this problem is too hard. The first thing that we want to do is to consider many copies of this state, and we want to study, like I said, how many classical or quantum correlations exist in this state. So we have this mixed state. This is shared between M parties. These are legal parties, but there's also this environment, like I said, it may or may not be purified. It may not be totally okay to call it environment. And we want to study how much classical correlations this state contains, meaning that I'm just going to refer to as a random variable shared between these legal players, uniform maybe, which is conceived from the side, and also how much noiseless entanglement in form of GHZ states is contained in this general state. Let me start by talking about a problem in classical information theory known as communication for omissions. Omissions means the state or situation where everybody knows everything. When there are these players here, each we sample some of this distribution, go to the classical distribution n times, and leave x1 to first layer, x2 to second layer, etc. And the idea is that parties want to talk to each other. Finally, all the parties will know the whole vector of observations. This state is called omniscience. Everybody knows everything. If we allow parties just talk to each other interactively, non-interactively, many times, problem is trivial. They will get to know everything. We have to introduce some kind of constraint to this problem. There are at least two ways of introducing constraint. What we introduce is we ask what's the minimum rate of communication to reach omissions. And in a paper in 2010, and Narayan showed that only one-way non-interactive communication is enough for parties to reach omissions, meaning that each party here sends just a message independent of other parties based on its own local data, one message transmission. And then that is optimal and they can reach omissions. And then they define the notion of distillable common randomness. So common randomness is a random variable which is shared by all parties and is uniformly distributed. And they introduce the notion of common randomness, which is the information, the rate of the total achievable rate, which is the rate of the total information, minus the consumed information, the consumed rate. So this is distillable common randomness. This is the rate that parties consume to reach omissions. So by this, let me talk about competency agreement. Now in this scenario, parties share this multipartite state in copies of the system such that the first layers observes A1 N systems and so on. Unlike classical case, if we allow for non-interactive communications, the situation will get much more complicated. And there is something probably to gain from general protocol. One can come up with complicated protocols. So we confine ourselves to non-interactive protocols, meaning that we allow each party to transmit only once. So what is it? So in this situation, what is the most general protocol, non-interactive protocol that they can do? Each party can apply a quantum instrument to its party. So quantum instrument is a quantum operation with quantum input and both quantum and classical output. And so parties will try to use that classical. Parties try to reach omissions on that classical output, and they're going to use quantum output of that instrument to reduce the transmission rate. This is the most general thing that they can do by non-interactive protocols. This problem quite naturally leads to the consideration of classical source compression with quantum side information, the very long problem that was solved in Andreas's thesis a long time ago. But this very setting requires simultaneous decoding. How Andreas solved this problem was by successive cancellation, finding extreme points of the polytope and doing time sharing. In this very setting, we cannot use that. We need simultaneous decoder, which was open since Andreas' thesis, and we managed to solve it in a previous work by where the main ingredient was sequence and joint totality. And so this problem that we studied before was new to this work. Now we have a guy here, which importantly has quantum side information. In the previous case, we could have had a guy who was able to observe communication between parties, but importantly now the guy has this quantum side information. So we end up distilling common randomness from this state where there is entanglement and where there is quantum side information. What is new? Again, each party will apply that instrument, creates quantum information, classical information, they try to reach formations at the classical part. The trick is obfuscation, how to get rid of this dropper. There are at least two ways of doing that. One is to do through this channel coding, we show this coding stuff, but the easiest for us was to just keep track of all the classical information between layers and use privacy amplification by smoothing entropies and use a couple of chain rules for smoothing entropies and do privacy amplification. So this part was we handled this part like that, and that's the proof that we have provided in the paper. Like I said, there might be other proofs. There exist other proofs, but we don't provide. Let's then look at this is the rate region finally that we get from this. So each party having this state, each party applies this instrument. So the state return into this state, which is X1 is the classical output of the first system, A1 prime is quantum output of the first layer. And then, like I said, they have made starting with many copies of the state, and then many copies of the CQ state, and this is the final state. This entropy here is evaluated on this state, and this is the rate, this is the minimum of the sum rates, RJ. These are the individual rates of parties that they transmit. And this sum rate has to be minimized, has to be minimized over this rate region, over this color, which comes from simultaneous decoder. And this is the consumed rate, and this is the rate region. This is the lower one we form for common for distillation of security. Going to so on optimality of rate region, I have an example, but I wish to speak for now. If I have time, I will come to discuss. Let me speak for now and go to GHZ distillation. Like before, now we have a general mixed state, n copies of this state shared between these layers. And we want to, the parties want to do LOCC until they end up sharing a GHZ state. As in case of in case there are only two parties, this leads to distillation of EPR pairs between two parties in the study and a long time ago. And in case the party is initial state is a pure state, we have already studied this in a previous publication. But now we want to study GHZ distillation from this general mixed state. I present two different approaches for this problem. One is we consider distillation of EPR pairs between any two parties, and then turning those EPR pairs into GHZ states. So that is the moment of exactly. I mean, the second approach is a making coherent approach where we take the protocol for security agreement and we turn it into a protocol that we can get GHZ states at the end of the day. So starting with the first protocols, I present the protocols to turn an even state into EPR pairs. The purest pure state environment is the purifying state. So again, I have this mixed state. I purify it to an environment. And by using the state regime, it is possible to turn this state, many copies of it, into bipartite states, EPR pairs between a distinguished party and all other parties. This can be done by state regime. And this is called entanglement homing. There's no, we can choose any party as our distinguished party, and we can do this there. The trick is that we have to make sure that the entanglement between the environment and this party is maximal. And by using this ability, we figure that, so what's happening, parties start merging it. So state merging makes this quantum source compression with quantum side activation. And when a party merges its state one by one to AI, it matters which state shares its state when. So it makes a difference on the achievable rates. And in order to make sure that this environment has the highest rate, we figured that the environment should merge its state in each run at the end of the protocol. And by doing that, we get EPR between these other states, and we can use teleportation to turn those EPR to GHZ states. So this is the rate that we get. This is the rate that we get for that. So this maximization is over the choice of the HCO, some distinguished party. And this is the coherent information given here. Our second approach to, again, distill EPR pairs and then turn them into GHZ state. We use something called entanglement of assistance. In entanglement of assistance, all parties held by LOCC, a distinguished party, to distill EPR pairs in between them. So let's say this is the in the initial state. So I have a large n-length block code. I took NT1 copies of n copies. T1 is a number between 0 and 1. From this many copies, all parties held A1 and AI to distill EPR. I took again NT2 copies of the state such that we can get EPR pair between A1 and A2, and so on. This EPR pairs should not be between a distinguished party and another party. Any spanning tree is fine. This is a station case. And this is less evident compared to previous case that by state merging we know the optimal rates. Here, what is known is just some lower bounds on the rate of installation. And then once we have these EPR pairs, we can use time sharing and we can get GHZ state. So this is the rate that finally we get. This maximization takes place for any choice of the spanning tree, making sure that we can see a sufficiently on EPR pair in all parties. And this is the rate region. This EA is entanglement was between party A and party J. The other approach that we pursue is making coherent. Notice that making coherent started in the works of Harrow, Delta, and Winter, and they take a protocol and they do everything coherent. What does it mean? I mean, if the protocol, if there is a network, a symbol, classical symbol in network, it becomes a computational basis of some inverse space. Functions will be linear operators on the inverse space, but obviously we are interested in permutations and isometries. That's why we are going to turn one-to-one functions into isometries or permutations into unitaries. And then we might need to then extend one-to-one functions to bijective functions to make sure that we have unitaries, and then this decoding operations will be, which are CPTP, that will be applied in the form of the Chinese string dilations. So it means that we have a bunch of unitaries that we can apply. So we are running perfectly well on positions. This means making coherent, and this is, for example, how some of the very important results in quantum channel theory are brought including the capacity of the quantum theory, quantum channel, which proved by Delta, by using exactly these things. So we take our protocol for for secret distillation and we make it coherent. We get this lower bound. So this is a mixed state purified to some environment. For technical reasons, we need to assume that the isometries are pure, meaning that there's only one cross operator, and we get this rate region. This is the distillable GHZ state from a mixed state, right? If I highlight it, and if I go back to the rate of the secret key, this is the rate of the secret key that I just proved a couple of slides ago. And this is the rate of the GHZ state, but we know that this side here is smaller than this one due to strong side. So we have extra quantum registers here that we don't have here. And for some time, we really try hard to see if we can get rid of those extra registers there. Those guys. But unfortunately, it was not possible. So for GHZ distillation, GHZ rate is potentially significantly less than the rate of the secret key. Makes sense, but again, we couldn't really get rid of the system. And back and forth, we could kind of justify why it makes sense not to be able to get rid of those systems. But looking into the same state for what's the most general state of a perfect secret key? Looking at this state, these are class. These X systems and these systems belong to repeated layers, and these the state of the environment. And if any state measures its X register, they end up sharing the secret key of very lucky. This is obvious. But is there a way of turning this state into a GHZ state that belongs to being able to undo the symmetry? We know that purifications are equivalent of symmetries, but we don't know in general if there is a way of undoing this unitary locally. And then by looking more carefully into this paper, we can learn that one can reduce the rate of the key here, the error so slightly, such that the whole thing will be turned into a PBT state totally unstable. So it makes sense that why we can get rid of those extra registers here. And I don't know if I have time, I will go back to here. Okay, let me quickly then go back to the secret key example. I don't know whether this is optimal or not. Looking at this example, A, B, C, they want to agree on a key, and this is the information of this object. What's the optimal strategy that they can? I mean, what's one potential strategy? Each party, A, B, C, they can measure this register, beta, gamma, and alpha, and they can broadcast it. By doing so, they are decoupling the environment because it's the environment that is dropping us. But by knowing beta, gamma, and alpha, the parties can undo these unitaries, U alpha, U beta, U gamma. And by doing so, by looking at the dimension of X register, they can end up with perfect secret key of rate log D, which is optimal because we can just calculate the local entropy of each party, which is log D. But by running our own protocol, in a simple example, when we assume these registers, the second register here is a qubit system, and the unitaries are either identity or three-dimensional quantum Fourier transform. If we apply our own conditions here, we cannot go beyond logity of common randomness between these players. So it means that this is the example showing that our lower bound is improving. So it's something that we probably look in the future, that what are the states, what is the structure of the states that our lower bound achieves common randomness, which is close to optimal. So yeah, I think like this, I want to stop. Thank you.
Thanks a lot. Questions for Farzin?
Yeah. People sitting at a round table maybe this evening, right? So can you achieve omni science by just sharing with your neighbor?
Sorry, again,
Remember the first part of the talk, where you want to achieve omni science, right?
I want to achieve only
Omni science.
omniscience. Okay.
Yeah. Anyway, so what is if you only share your information with your neighbor? Can you then achieve this omni thingy? Right? They can just come to their neighbors, maybe you can close it up.
I mean,
Your protocol had all the access,
yes.
but so if they only can share information with their neighbor, can they achieve anything that CO?
I mean, this is at the end of the day, a certain more code. If this guy doesn't get any message, this won't be able to request.
Yeah, but a circle.
You mean these three parties? These
No, everybody goes to the right.
Yes.
And you close it to the
One
circle.
by one.
Yeah. What can you achieve? Because that's very realistic. Somehow.
No, it's a simple. It is by simple Stephen Wald argument, we can say that that's not possible.
Now imagine this guy sends something to this one, then this guy, or these two guys communicate. So these two guys know, this guy sends something to this one, this guy doesn't know X time X two. This guy needs to send something to this one.
That's not going to be possible. That gives rise to something new, but that won't achieve all missions. And I think we can see this.
2 rounds or 3 rounds? I'm just asking you, there is some room for it.
I mean, I love to write it down and see how it works, but definitely it's something different. I mean, there's also other interesting questions that what if a subset of parties are helping other subsets? This is something that we are in a new project we are working with Andreas on it. Please go.
Yes. Yeah. And so regarding optimality, clearly with the normal that you got, which is unknown.
Unfortunately, I mean, we can come up with multi-letter, upper bounds, but we don't have any useful upper bounds. And that's why we came up with examples showing that, with lower bound can be really bad.
More questions?
Yeah, maybe I have one. Then, so, what about the classical case? Because you showed not the secret key distillation, for example, right?
Yes.
I also mentioned this classical result. Is that optimal?
Yes, this is optimal. This is optimal.
Nice.
This is optimal, and then.
But this is, the classical, the simultaneous decoder in classical and processor is just trivial, right? It's not a big deal. It's only in quantum information that gets huge deal.
But are you saying your result is not optimal because of the simultaneous?
No, I don't know. To achieve our results, we need to have simultaneous decoder.
Yeah.
But in classical case, it is optimal. They have also converse bound showing that it is optimal. But we don't have that we have the simultaneous decoder, but we don't have that.
How does this formula look like here? Similar?
Yes, they look very similar, but we have quantum register. I mean, we know how to go beyond our current results by playing around with that quantum part. For example, we can consider that quantum system in encoding also. Like there's some work that Zara has done with Andreas and others, and then they are considering such scenario. Yes, we can go a little bit beyond that.
Okay, good. So let's thank Farzin again.